Okay, we're going to talk about relative velocity using a problem with baseball. Okay, so the issue or the setup here is we have a shortstop, which is a position in baseball, and this person is throwing a ball. He's running, and as he's running, he's throwing the ball, and he's going to throw it to the catcher, and the catcher is not moving. Okay, so that's the basic gist of the setup. Now, of course, we would like to find out like the different relative velocities, like maybe the shortstop versus the ball, the catcher versus the ball, the shortstop versus the catcher, et cetera, et cetera. Like multiple like different types of combinations we could possibly want to find out. Okay, so what I want to do is I want to show you how to solve one of these problems using like a method that I came up with that I think is pretty interesting, and that is what we're going to do is we're going to figure out, number one, what are all the objects involved in this problem. So number one, there is a shortstop, there's a ball, there's a catcher, and lastly, and this may be something that you might forget, and that's the earth or the ground. So, if you normally are, traveling in a car, going 50 miles an hour or whatever, well, that's relative to what? The earth or the ground, okay? So usually when we talk about speeds or velocities, it is usually relative to the earth, okay? So when we do these one of these problems, we want to make sure we obviously include the earth. Okay, so we have these four objects, and what I want to do is I want to build like a graph, okay? And then we're going to associate each object with another object in the graph using some arrows, okay? All right, so we're going to do that now. So what we have here is I'm going to go ahead and draw this out. We have the ball. I'm going to put that in a square. And first, so B is ball. S is the shortstop. Over here we have the catcher, C. And then down here at the bottom we have the earth, or E, okay? And so what I would like to do is I would like to draw some arrows between these objects as appropriate. Now, before I do that, I would like to just have a small aside. Let's imagine I already had the velocity, let's say, of A relative to B. Okay, this, like I said, this is just an aside. And let's imagine that this vector looked like this. Okay. And imagine it was like 3 meters per second. So that was the magnitude of the vector, and as you can see, it's going east. So what I'm going to do above is I'm going to create like an A, for example, an A entity and a B entity, and based on this vector here, what I would do is I would draw an arrow like that from A to B because the velocity is A. Of object A relative to object B, and so I would just do A to B because it's starting at because A is relative to B. Okay, and so this here would be there would be some vector here, and it's 3 meters per second. Now, what if you wanted to switch that? Meaning you wanted basically something like B to A. Right, where you're saying I want the velocity of B. I want the velocity of B relative to A. Well, how could you do that? Well, basically, all you have to do is just take that and flip it around. So it would look like just like this. It would look at velocity of B relative to A, and you would maybe put the point here and then the arrow here, and it'd be 3 meters per second. So basically what I'm trying to show here is that we're gonna create entities, in this case here A and B, and we're gonna draw it from if it's A relative to B, we're gonna start at A and then we're gonna go to B. But for some reason, if you did want the arrow in the opposite direction, you just invert it. Just invert the vector. Okay. All right, and I'll show that here in just a second. So that was a small aside. All right, so I'm going to erase this, and then we're going to get back to the problem, because we're going to use these techniques in this problem. All right, so here we are. Here's the problem. We have a ball, a shortstop, a catcher, and the earth. And the problem is, and I'll just sort of lay this out, is that there is a relationship between the ball and the shortstop. And I'm gonna draw the arrow like that. So this, and the reason I drew the arrow like that is because we have the velocity of the ball relative to the shortstop. Okay, so that's why I started at the B and I went to S. Now, what this vector looks like, now I just drew an arrow, but that arrow is not a vector. That's just a line in this graph, okay? But what the actual vector looks like is, and I'm going to draw that here, is it's going straight down, and it's 6 meters per second. Okay, so that's that vector. So we have that one vector. The next one I have is between the catcher and the earth. So that looks like this. So this is the velocity of the catcher relative to the earth. And once again, the arrow, as you can see, goes from C to E. And it's in that direction. Now here, the catcher is not moving. Okay, the catcher is not moving. So I'm going to draw a dot, meaning a zero vector. Okay, so it doesn't actually have a length or a magnitude associated with it. And I'm also going to write next to it 0 meters per second, just to be obvious. Okay, so the dot represents the vector, which is a zero vector, and then the length or the magnitude of this vector is 0 meters per second. So that's the velocity of the catcher versus the earth, meaning he's not moving. Now, the other thing is we have this one as well too, between S and R. So this is the velocity of the shortstop relative to earth. And remember, the shortstop is the person running. So remember, the shortstop is running, and he has a ball, and he's throwing the ball to the catcher. So that's it. There's a shortstop, and there's a catcher. So the velocity of the shortstop versus relative to the earth, and the problem states that it is a vector going due east. So the shortstop is running due east, like I said, relative to the earth, which is a common reference frame. But the problem is I don't know. So that's its direction, but I don't know its speed. So I'm going to write a question mark right here. Meters per second, because I don't know what the speed is. But I do know the direction. Okay, and then the last piece of the puzzle is between the ball and the catcher. So if I go between here, like that. So this is so the arrow looks like this. And so this is the velocity of the ball relative to the catcher. Okay, and so the problem states that, so there's some vector, and I'm going to write it as a dot and maybe a question mark next to it, meaning I don't actually know the direction of the vector, so I'm putting a question mark next to that. But I do know that its speed is 9 meters per second. Okay? So this is the setup. And so I have my 4 entities: the ball, the shortstop, the earth, the catcher, and I have the arrows that link them together with their velocities. What I would like to find out is I would like to find I would like to find out that actual vector there, like its direction, and I would like to find out its length or magnitude. The other thing I would probably like to find out is, what does this look? I'm going to change this. What does this vector look like? Okay. So this is the velocity between the velocity of the ball relative to the Earth. Okay, and here it wasn't given no information was given in the problem with that. Okay, so maybe that's also something I would like to find out. Those three things, and once I have these three things, then I have this entire diagram finished. In any question you could possibly ask, you could solve it. Okay. All right. So what I want to do first is I want to start off with the velocity of the ball relative to the Earth. So let's do that. So, and I'm going to end up erasing this, but just for temporary sake, I want to find out what this is. Okay. And in order to do that, you could say I have a vector here which is in red. You can say, okay, well, maybe it's that. Maybe it's the two blue arrows. So V of B over E is equal to V of BS over VSE. The problem with that is that you're missing this other the velocity of the shortstop versus the Earth. I don't know its length, so I can't actually do this problem, at least not right now. So that's not doable. But what I could do is, what if I did this instead? So I want to find the velocity. Basically, I want to make a connection between B and E. So meaning the velocity of the ball relative to Earth. So instead of doing it directly, I could just do it indirectly. I could just go from B to C, and then from C to E. Okay. Now the problem with that is, well, let me just go ahead and write this down. Okay. So I want the velocity of the ball relative to Earth is equal to the velocity of the ball relative to the catcher plus the velocity of the catcher relative to the Earth. Okay. Right? So, the velocity of the ball relative to Earth, I don't know that, but I do know, so V of B over C. Well, so the problem is that so these two vectors here that I'm looking for, V of BC, let me just quickly, this one and this one right here, I don't know its actual direction. Okay, so that's its problem. But for both of them, I do know their speeds. Okay, so what we're going to do then is we're just going to write their speeds down instead. So the velocity of the ball relative to the catcher is 9 meters per second. And the velocity of the catcher versus the Earth is 0 meters per second. Okay, so I have 9 meters per second plus 0 meters per second. Now, you want to be careful when you're adding these vector velocities, because here's an example. Let's say I have a vector that looks like this, and then another vector that looks like this, and say this is 3 and this is 5, and you want to add them up. Yeah, because they're going in the same direction, you could say 3 plus 5 is 8. But what if you had a vector that looked like this, 3, and then the other vector looked like this, 5? Once again, you're adding them. The resulting vector is going to be that. So that's not 8, is it? No, it's not. You have to do some trigonometry. Well, you'd have to do Pythagorean theorem. You have to do 3 squared plus 5 squared, take the square root of that, right? So my point is when you're adding these velocities from these vectors, be super careful as to the direction. The reason I can actually add these directly is because, well, I was given the 0 meters per second, it's a 0 vector. So it's essentially nothing plus 9 meters per second. So basically you have whatever this 9 meters per second is, let's say it's going like that. We don't know where it's going. But the other one is just 0, right? So no matter where this vector is actually pointing, right? No matter its direction, you're just adding it to the 0 vector. So no matter what it is, you're going to end up with 9 meters per second. Okay, so this ends up being 9 meters per second. Great. And so that's the velocity of the ball versus the earth, which is right. Maybe I'll change that to green. So this is 9 meters per second, which is cool. Okay, so once you have that, now you can actually do this thing. So now we can do this. Let me show you this. Now we can go from here to here. And let me show you how that works. So I'm going to say the velocity of the ball relative to the earth is equal to the velocity of the ball relative to the shortstop plus the velocity of the shortstop relative to the earth. Okay? So let's start from there here. What is the velocity of the ball relative to earth? Well, we just did that. That's this guy here. So it's 9 meters per second equals. What's the velocity of the ball relative to the shortstop? Well, we already have that. That's this vector going down. That's 6 meters per second plus. And then this other one here, it's some vector going due east, but I don't know its speed, okay? But what we can do is we can take this guy and we can draw a triangle from it or do some trigonometry. So I'm just going to start. It doesn't really matter which. I have these two vectors, right? It's the 6ms vector, and then the one that's basically it's the arrow that's going south and the arrow's going east. It doesn't really matter which one you do first. You're just adding the two vectors together. So it doesn't. You're like, which one should I use first? It doesn't matter. So I'm going to do this one first, and then from there I'm going to add this one on. Okay. And then once I have that, then this is the resulting vector is the one here. Maybe I'll actually do dots on it just to show you so it looks slightly different. Okay. So that's the resulting vector, or VBE. Okay. So the one going down is 6, and then the one over here is, I don't know how long it is, so it's question mark. But then how long is it? Well, we already figured that out. We did that in the previous step, and so this is 9. So that's 9 meters per second, 6 meters per second, and this other one. So, and this is an orthogonal triangle. It has a right angle, 90 degrees. So what I would like to do is I would like to find out maybe some of these angles in this triangle. Okay, so I'm going to call this guy phi here up at the top. And so if I do the cosine of phi, and so of course cosine of course is adjacent over hypotenuse. The adjacent side is the 6, the hypotenuse is a 9. And now if I hit this with a inverse cosine, so a cosine inverse, on one side, and then of course you have to do it to the other side as well too, you'll end up with phi equals to 48 degrees. 48 degrees. So this is 48 degrees. If that's true, then the other angle is 42 degrees, because 48 plus 42 plus 90 is 180 degrees, which is what we should have for this triangle. Great. So now that I have two sides plus all three angles, I can now find out what this question mark is. And so, well, I can just do it like this. I can say the cosine, which once again is, and I'm going to write 42, I'm going to actually just use the bottom one, 42 degrees is equal to, and remember cosine is adjacent, which is, in this case here is the question mark, over 9, and I'm looking for the question mark, so we just have to rearrange this. 9 times cosine 42 degrees equals 6.7, 6.7, and this is in meters per second. So this question mark right here is 6.7 meters per second, which is, maybe I'll write it in red here, 6.7. Let me just erase this a little bit. So that's this guy here. Maybe I'll make it red, sorry. 6.7 meters per second. Let me actually erase this question mark because I know what it is. Cool. All right, so that looks good. Now, So I have that vector is completely solved. I know it's direct. So VSE, the velocity of the shortstop versus the Earth relative to the Earth. I have its direction, and now I have its magnitude. And then VBS, I have that one as well too. VCE, I have that one as well. Now VBE, so that's this guy. So this one. Sorry, I'm just looking for something to draw. Let's use this one. This is actually this vector, right? This is that's it because we're using VBE, right? So VBE is that that vector there. Okay, so it looks like this. So it looks like maybe if I draw like this, something like that. Right, it's going down, 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 something like that. And it's 6 on the side and 6.7, 6 vertically down and then 6.7 horizontally. Okay, so that's great. So now I actually have that vector right there. The last one is this one up at the top. So this one like right here. Okay. All right, this one up here at the top. So what is that? Well, it is the velocity of the ball relative to the catcher. Well, what is that? What is it? Like, what's another way of saying that vector? Well, couldn't you just say it's the velocity of the ball relative to the Earth plus the velocity of the Earth relative to the catcher. Okay. Basically, I'm going to go this direction. So I'm going to go, so here it's this. Let me just change it to this. Sorry. I'm going to go this direction from here and this. I'm going to add those two vectors, okay? That's VBE plus VEC. Now, if you're looking at VCE here, it is actually the 0 vector. So technically, this line looks like this. You could actually write the arrow in both directions because it's a 0 vector. So it doesn't, if you reverse it, it's still the same. Okay. So I can go from B to E, which is this one, right? Look at the arrow. And then I can go from E to C, which is this one. And so what does that look like? Well, BE looks like it's that vector. Remember that one, the one we just did? And then VEC, what does that one look like? Well, that's just the 0 vector. So then what does VBC look like? Well, it's just that diagonal vector that's pointing down plus the 0 vector, which is just that. Okay. And so yeah, so then you just take that and you plug that back into this guy here, and maybe I'll erase it. And then come back to here, and then maybe I'll make it red. And then yeah, that's this vector here, so I'll just draw something like that, and then there's the line there, and then there's that, and then, yeah, that's 6 on the side, 6 meters per second, meters per second on the side, and 6.71 on the horizontal, which makes sense. So with this, so just to recap, we basically solved everything. So we have all 4 of these entities: the Earth, the shortstop, the ball, the catcher, and we drew arrows between them depending on the direction that we had. So if it was like V, B, C, that means the arrow went from B to C. If I wanted to the other way, it would have to be C, V, C, B, where the arrow started at C and it ended at B. Okay, so let me just erase this. So to solve one of these problems, once again, what I would do is obviously read the problem, try to do a small sketch of the problem. Maybe if it's a car or an airplane or people running or whatever, just try to sketch it out. Number one. Well, read the problem. Number one. Number two, try to sketch it out. Number three, try to write down all the entities that you have, which in this case is shortstop, ball, catcher, earth. The next step after that is try to draw this graph that I have here, and then draw the arrows between between the objects. Okay, and remember, you can't traverse, you can't go from say B to S unless the arrow is pointing in that direction. Okay, and if it's not pointing in the right direction, well, you can invert the arrow, but then you also have to invert the vector as well too. So it can definitely be done, but just remember to do that. And then yeah, so then once you have your graph and all your arrows and everything in place, then you basically just have to use algebra / trigonometry to just solve for the things that are missing. And then that's basically it. So yeah, so doing relative velocity problems can be difficult or tricky, but I think if you look at it graphically using this graph approach, it might make the solutions easier. So hopefully that was useful, and see you later.